Okay, so uh, starting from today, I will start the uh, the review of the recent developments. Okay, so hopefully we will maybe after 3 or 4 weeks, uh, like for example, the 3 weeks you will have the another second homework, right? 21st April, and then after that also the same presentations and a little bit course, and then the third homework presentations, or maybe I will arrange that if the time is not possible, then maybe after the third homework you will directly go to the final, because I think for the final exam at least we need 2 days, like one day using the 1 hour class. Maybe you can present maybe some students, maybe 4 or 5, and then the next 2 hour classes will be the rest. But I think I need to have 2 weeks, because I think there will be 3 or 4 that still need to have a presentation left. So that will be around month of maybe May, the end of May, and maybe the first week of June. So 2 weeks for the final presentation. So for today, I'm summarize some of the interesting topics that really develop really well in the smart materials. So if we go through the review of recent developments, okay. So this is the common smart material definition. Okay, like yesterday I asked you the smart materials, and then the second one, the advanced one, right? So if you talk about smart materials, the materials need to be smart, right? The first smart material definition, or we call the common smart materials, it is smart materials that are already available on the market, people already using it. So it is just as simple as you have the materials, you have the stimuli, and the materials can behave or change its property depends on the stimuli. Okay, it can be a temperature, light, pH, or any other external stimuli. So this is the common definition. Okay, so smart materials is respond to external stimuli in a controlled manner, or you can program it, you can train, okay, to conduct a predetermined task. Okay, this is actually difficult to define because the definition is too general. So the more advanced definition is we can say that it can have a smart behavior. So it's not like a static object anymore. It can be a dynamic, like more or less like a living organisms. Okay. So when a material sends some stimuli from the environment and reacts in a useful, reliable, and reproducible manner, so it can be really measurable. And also, besides of this definition, you can also say that the advanced one, it can have multifunctionality. So it may have like one property that change, but maybe it can have more than one. Okay, like the video like I showed you before, the extreme biomimetics. So it can have, for example, the fiber optics. It can have a good light property, but also it can have a good mechanical property that it can change shape, depends on the environment. Okay. So that is the smart materials. And the smart material itself, the definition, it is not stop. Okay, it's not a full stop. It's still developing. So maybe in the future there will be a new advancement, new technology, and maybe the definition also change along the way. Because until now, several group of research, they define differently, but it's not really that different. Okay. And from that smart materials, there are at least 4 topics that really take, in my opinion, a lot of development. Okay, it's the self-healing, smart sensing, shape changing, and color changing. So let's start from the self-healing. So self-healing, it can be thought of the material responding to damage and then automatically initiating some form of repair. Okay, and there are a lot of mechanisms. This is just a few examples of the mechanism. The first one, if there is a crack, okay, so the first one is using the capillary, okay, or fibers, okay, inside a composite, okay, and then inside that capillary there will be a monomer, okay. So when crack happen, and then the fiber or the capillary also crack, it will release monomer, and usually they have also curing agent nearby that capillary. So when monomer release, it's also releasing curing agent, and they will react. Okay? There will be a reaction here, and it will be self-heal. Okay. And then the second mechanism, it is similar with the first one, but it is using a catalyst to make the process or reactions more efficient and faster in some way. So the catalyst will lower the barriers of the reaction, meaning the energy that need to be used is reduced, and it will allow the reactions. Usually, the energy based on the temperature or heat. So this is the crack here, the left side. See, this is the crack, and the crack getting bigger, and then it's reaching this circle. It's having the monomer, so it's releasing the polymer, and then it will fill the crack. It will fill the crack. Third mechanism is using. Actually, this is similar with the capillary, the first one, but it's more complex. They are using a microvascular networks. Okay. So they are using this microvascular as the monomer, okay, as the monomer encapsulations. And when crack happens, it will polymerize the monomer, and based on the design, this will be achieving a more efficient results compared with the first one. And the other, I don't have the picture, but actually I have seen before some research. They are using the we call metallo-supramolecular polymers. So it's like a metal, like imagine a wire, but when you crack or when you broke that wire, it has the capability to self-heal. Okay, so in this study they developed for pipe. So after a pipe of the composite is cracked, the wires stretch, but when you are hitting the wire will come and pulling the crack together, and the matrix in the composite will melt and blend, and then it will be healed. So you can use also this kind of self-heal. So using like a wire, so the wire will stretch and goes back to the original shape and helping the structure back together. And then this is the mechanism 5. This is for the anti-corrosion. So imagine this is the substrate, the metals. Okay, usually in the piping in oil and gas, one of the difficulty is to control the corrosion, because corrosion, although you can say that, oh, we have stainless steel will have stain. Okay, there is no stainless steel really stainless. It will have stain along the way. Okay, it goes also for any piping in oil and gas usually, or any installation system using pipe. Okay, and corrosion, despite maybe you having chemistry class and maybe some parts dealing with corrosion itself is really complicated and really having a lot of content. In some university, corrosion itself is one course. It's about corrosion. So how to prevent corrosion, how to control corrosion, and why, and the process why corrosion happens is really complex. Okay, but here is they try to make some coating. So they use this coating in up here, and this coating, it has the monomer. Okay, this circle, the red circle. I think this is using the HDI, the hexamethylene deassociated. Yeah, this is the some microcapsules. There's red one. So when the coating crack, okay, before the air reaching the metal substrate, the crack in the coating, it will help to close this crack. So crack, and then there will be a reaction with water. So maybe this is piping underwater, okay, for application piping underwater. So water will react, and then it will help the coating to self-heal. But it didn't mention how fast the reaction, because in corrosion, okay, if you're interested in corrosion, in the water plus salt plus natrium chloride, the chloride ions, it will make the corrosion happen faster. That's what I can tell you, just a short. Okay, chlorine makes the corrosion process faster, so we need to prevent any chlorine ions actually. Okay, so I'm not sure how fast this is going to happen, but they need to think of that to make sure it will heal before long open. Okay, so this is the mechanism, the fifth mechanism. And then the next one is the smart sensing. So self-healing and then smart sensing. You can also think this as maybe inspiration or idea in the future. So smart sensing. So this means the material, it can sense any stress, loads, and other maybe external factors. And usually, to make it easier, maybe in the just engineering as a factor. Okay, so for example, these loads, stress, compressions, like a building, they need to have other external factors, right? So if they can detect any deterioration or any crack before the crack propagate and make the building rupture, we can prevent. So this is like a prevention system. Okay, so if we can prevent at the early stage, we can prevent any catastrophic failure, any rupture, any broken device, and so on. So the mechanism. So smart or self-sensing, it has the several functionalities. Okay, So it can sense the property, and it can be concrete, plastics, textile, paper, metals, composite, and can be used to implement self-diagnosis. So they can give signals, okay, self-healing or other type of smart behavior. So it also can be having this self-healing, also self-diagnosis, and also other maybe functionalities. So we can also call this as a sensing skins. So we imagine, because our skins, we can sense anything that come to our skin, right? Like it is fluid, it is hot, cold, right? And we can code these sensing skins to any structure or component. And this is because of we call the FBG. Okay, this is the standard for the mechanism. So it's the fiber bragg grating. Okay, so fiber bragg grating, you can see the picture here. It's like having like a fiber inside this composite. Okay, so this is composite, or this is a polymer sheet. It has the optical fiber and then fiber grating in the optical fiber. It has the electrical cable. So if the sensor, so FBG is a sensor, so if it is embedded in the composite structure, a change in the strain in the structure results in the grating being subject to a similar strain, and then it can be quantified. So you can quantify the strain or any stress that you apply to this self-sensing or skin sensing, and then it can deliver a signal because it has the electrical cable here, and it will give the early warning. For example, if the crack is propagate and it is dangerous, okay, so at the early stage of that crack, it can give the signals. I have some video here, but maybe I need to. Yeah, this is the company that's selling the FPG. So through the development of the FPG, the self-sensing or this skin sensing or smart sensing materials becoming more and more advanced or developed. Because through that FPG, you can see that when it is having a stress or strain, it will give a signal, the wavelength back to the detector, right? So it has a special grating system in the FPG. When you start to giving optical light, it will reflect some part of that light. So when you are changing the structure, the light also change, and it will detect any change in the system, and that's how you can at least having an early warning system. I think it can also use in any mitigation, earthquake mitigation for buildings. I'm sure they are using some sensor, and probably they are using mostly the FPG, because this is widely used for the early warning system. So that's the mechanism. So that's the smart sensing. So smart sensing, it can be any. So aside from the sensing, it can also have, for example, how to maintain that it can have a good functionality. For example, if the smart sensing material is broken, what will happen? It will be dangerous, right? So sometimes they need to have the smart sensing itself, the polymers, the composite, it can be self-healed. So if it is like a crack, it can self-heal. It's also possible. Okay, smart sensing, and then the shape changing. I think shape changing, we already talked a lot of this shape changing, but I want to make some emphasis. So shape changing, it's the most major, which means it is well developed. Okay? It's already well established. Okay, as smart materials. Okay. They exhibit the property of remembering their original shape, to which they return after deformation when subjected to a thermal or other stimulus. There are at least two terms that have important meaning in this shape changing. The first one is shape memory effect. I think this already being taught at the early courses. So the shape memory effect means it can be deformed by application of external stress and fixed in a second, okay, temporary shape. And this temporary shape is retained until the shape is exposed to stimulus like temperature, and it will be going back to original shape. Okay? That's the shape memory effect. The other is called the shape changing capability. So this is also you can say a new term. So shape changing capability means the materials, it can change their shape gradually. So it can shrink or bend as long as they are exposed to a suitable stimuli. They recover their original shape as long as the stimuli terminated. So it's a little bit different, okay? But it means the shape can be changed all over the time as long as there are stimuli. When the stimuli removed, they will be back. It's different from the yesterday questions. The yesterday question is just only applying the force, right? Which means it's not smart material, it is just elastic deformation. Okay, that is shape changing, and then the last one is the color changing material. So usually structural color materials, it's based on we call this the principle of thin film interference and colloidal photonic crystals. Okay, the details I cannot told you in this course, but within these principles, it will offer more durable and brilliant colorations than conventional pigments like using colorant. Okay? So this will inspire the artificial color changing sensing materials with superior property. And this thin film and colloidal photonic crystal, it can be observed through nature also from any color changing animals or plants. There are some that have this property. and the difference between each interference effect is from the color alteration will rely on the change in the thickness or reflective index, okay, in the film. Okay, as I think you know reflective index, right? So you have like some material can have light, and it can be reflected, it can be goes here, right? So reflective index is a ratio for that materials, okay? Ratio how can the light can be reflected or not. It depends on the reflective index. It can be induced by several stimuli. It can be photo-induced, it can be magnetically, chemical, electrical, thermal, okay? And all of this, okay, the color changing materials. So I will go back to here. So we have at least four big topics: self-healing, smart sensing, shape changing, color changing. So each week I try to cover one by one and goes deeper into some research and how they develop. So I will explain more details about the self-healing, smart sensing, shape changing, color changing. But at least for now, okay, these four big topics is quite fascinating or quite developed. Okay, it has been, I think, and for this for all this type, okay, it doesn't mean you need just focus on biomimetic, etc. It doesn't. It's not necessary. So you can have a lot of combinations, a lot of materials here, a lot of process also. So you can have maybe these small materials it's already having multifunctionality, okay, and you may find in any paper that has this topic, it's really usually complicated process, but if you are going through the key information, you will understand, oh, this is just a simple research actually. The difficult is usually in the process, because most of these materials, they are using the polymers mostly, because polymers you can utilize as long or as you want, okay? Like how the shape will change, how the property will change. Polymers have the capability to do that, and polymers have a lot of possibility because it has a lot of monomers, functional groups, right? You can have a lot of variation, and yeah, and also the biological property, because biological property mostly they are polymers, right? Like our body is polymer. Some parts it's peptide, right? It's polymer. Protein is polymer, right? Carbohydrate is polymer, right? So we are polymer. Yeah, you can say that. Okay, so I think we can stop here. Next week I will go deeper one by one in these topics, and don't forget the 21st April for the homework. Okay. Okay. Thank you all. See you in the next course.